This semester, in the spring of 2020, our team completed our capstone projects as part of the Industrial Manufacturing Systems Engineering program at Iowa State University. The team members of Group 10 are Levi David Schofer, Connor Gord, Marie Loy, and Alex Shepard. Our team completed a project in an unnamed company this semester. This company's facility was designed to utilize the cellular manufacturing model. For our team's project, the objectives were reduce the footprint of three similar cells, increase throughput, reduce labor hours, and reduce material handling within the cell. To learn more about the process and understand the flow within the cells, we conducted a work sampling study and completed a spaghetti diagram. We also performed a line balancing task analysis to ensure all operators had equal portions of the cycle time to complete.
First, a work sampling study was conducted by team members across three similar cells. The machine status levels were recorded every 10 to 12 minutes. There were three categories in which the status levels fell. The status levels and categories were as follows: running, which fell into the value added category, idle action needed and idle no action needed in the non value added and not necessary category, and lastly, loading, unloading, inspection, and maintenance or setup, which fell into the non value added but necessary category. Once all of the data was collected, the team calculated utilization percentages for each machine based on three categories. The table shown is an example of the utilization report. For example, the utilization for machine 1 was conducted over 97 observations and showed 10% of value-added tasks, 89% of non-value-added and not necessary tasks, and 1% of non-value-added but necessary tasks. This data allowed the team to see where machine utilization could be improved and if bottleneck operations were being starved.
The second engineering standard we used to understand the cell processes was a spaghetti diagram. We sketched a layout of the cell and numbered all the machines and workstations that operators would visit. As the operator traveled from each machine or workstation, we documented the assigned number. We were then able to create the spaghetti diagram. During the observation time, we also recorded the number of times each operator used the overhead hoist to move the part. This helped us identify where the operators were handling the parts the most and areas that we could work to improve. Finally, we conducted a time study to find the cycle time for all tasks completed in the cell. We then validated the data we collected with standard work documents provided by the company. This is an example of a Gantt chart we created for each of the operators in the cell. It visually displays each of the tasks with its corresponding cycle time. After comparing the Gantt charts and identifying the bottleneck operator and task within the process, we decided to rearrange responsibilities across the operators to balance the workload. This allowed us to ultimately reduce labor hours in the cell while maintaining the cell throughput.
After analyzing the data and discussing with the company, the team created this final cell design. This design incorporates aspects of our top 3 alternative designs that together address all the project objectives. In this design, the cells rotated 90 degrees, moving where the raw materials and finished products are dropped off and picked up. We also brainstormed a new way of handling parts, through the use of roller tracks between certain workstations to reduce the number of times the operator used the overhead hoist. From our line balancing task analysis, we found that a new machine can be added to the cell to help balance the workload between operators. By rotating all 3 cells, we were able to reduce the total floor space by 8%. The new way of handling the parts in the cell with roller tracks reduced the overhead hoist usage by 25%. Due to the work cell tasks being rearranged amongst the operators, the labor hours required in each of the 3 cells was reduced by 25% while still maintaining current throughput. Overall, the 3-year return on these improvements approximately equals the upfront cost of implementation.